Bismillahirrahmanirrahim. Assalamualaikum and very good morning. Okay, the how the impedance matching is done. So this is basically the basic block diagram of a matching network. So usually what we have seen, we have a generator, and then we have the transmission line, and then it is terminated by a load, whether it is less like L or it is open or short circuit. And this is the transmission line with the length L. So the transmission line is directly connected to the load, right? So as we have known that there will be a standing wave for the signal within the transmission line due to the reflection at the inner surface of the transmission line. Therefore, there could be power losses during the transmission. So therefore, to minimize or to avoid reflection or power loss, a matching network is introduced in between the transmission line and also the load. Okay, there are three types of matching network. It is single-stub matching, quarter wavelength transformer, or lump elements or L-section network. Okay, so as mentioned, the impedance matching network is placed or is introduced in between the load and also the transmission line, and it is the matching network values or the parameters usually designed so that the impedance seen looking into the matching network is Z0. So it is assumed that the load impedance will be matched to Z0. So in this case, when we introduce the matching network, the reflections on the left of the matching network, okay, on this side, will be eliminated, although they could be multiple reflections as well after the matching network to the load. Okay, however, the effect will be minimal if compared to the losses within the transmission line itself. Okay, so why we need the matching or tuning? Okay, matching, impedance matching, also known as tuning. So to ensure maximum power delivered to the load. Alright, so the line is matched to the load, so the power loss is minimized. Besides that, impedance matching sensitive receiver components such as antenna, low amplifier, so it can improve the signal-to-noise ratio of the overall system. And also the impedance matching in power distribution may reduce amplitude and phase error. Okay, so it can improve in terms of the signal-to-noise ratio and reduce the error in amplitude and phase as well. Right, so there are four main factors that need to be considered in the selection of type of matching network, okay, to be used. Okay, first, in terms of the complexity, so the simpler the design, the better. So as long as it satisfies the basic requirement or specification, and it cost saving, smaller in size, reliable, less lossy than the more complex design. So next, the other factor is the bandwidth. Okay, so any type of matching network can ideally give perfect match or zero reflection at single frequency. However, if the system involves multi-bands or more frequencies, so it is preferable to have a system that can match for a broad band of frequencies. And in terms of the implementation, depending on the application, okay, sometimes, for example, tuning stub will be much easier to be implemented in waveguide if compared to other techniques. And lastly, the adjustability, or is it easy to modify or to amend the structure or not. Okay, sometimes in some application the matching network may require adjustment. Okay, sometimes there will be optimization process in so that the system can be improved further. So the system with more flexibility or easy to amend will be preferable if compared to the rigid or fixed structure. Okay, we are going to look at the first technique in impedance matching, which is the single-stub tuning. So in single-stub tuning, it will use a single open circuit or short circuit length of transmission line or a stub. Okay, from the figure, you'll see that these are the stubs. Okay, additional element that included in the system. This is basically the matching network introduced into the system in between the transmission line to the load. All right, so it's either connected in parallel or in series to the transmission feed line at certain distance d from the load. Okay, the stub is introduced at distance d from the load. Okay, stub is convenient to use and it can be easily fabricated if compared to lump element. Okay, lump element in which you need to deal with the circuit. Okay, lump element circuit, so it will be more complicated if compared to the stub element. Right, so two main parameters that need to be considered in single-stub tuning network. The first is the d, the distance from the load to the stub position. Okay, this is the stub position. So the distance d from the load, and also the value of susceptance or reactance provided by the stub. Okay, so the value of susceptance or reactance provided by the stub. Okay, so there are two configurations. The first one is the shunt stub. Okay, this is the left figure, basically the configuration of shunt stub, while the right hand side is the series stub. So for shunt stub, it is preferred for microstrip line or strip line, while the series stub is preferable for slot line or coplanar waveguide. Okay, more details on the shunts and series stub. Okay, so the shunt stub, the distance from the stub position to the load is chosen so that the admittance Y seen looking into the line at distance d from the load is in the form of Y0 plus JB. Okay, so then the stub susceptance is chosen to be negative JB so that we can match this one. Okay, resulting a match condition. Okay, while for the series stub, the D is chosen so that the impedance provided by the stub at a distance d from the load is in the form of Z0 plus Jx. So the stub reactance is chosen as negative Jx. Okay, so to simplify this or to remove the imaginary part so that it results in match condition. Okay, now let's look at the processes or the steps involved in designing a single shunt stub. Right, so the shunt will be the parallel stub to the transmission line. Okay, this is the transmission line with the load. So we introduce the matching network in parallel to the transmission line or the shunt stub. So at this point, it could the stub could be an open or shorted stub. Okay, so the first step is to plot the normalized impedance, load impedance. So ZL, as usual, once we have the ZL, so we can find the normalized ZL and plot it, and as usual, draw the SWR circle from the center of the Smith chart, and then plot the normalized admittance. All right, so admittance is the translational of the ZL, or it is in the opposite side of the ZL, and then mark the YL position, and then mark, you can drag down the you can extend a line from the center of the Smith chart to the YL point using, and look at the position using the towards the generator. Okay, the wavelength towards generator. Right, next, draw the 1 plus G beta circle. Okay, the Smith chart. So here is 1, here is 0. So draw 1 plus G beta circle. So the radius is 1, the real part is 1, and G beta circle. So JB circle, so B representing all the susceptance value that having the same radius R. Okay, and then mark the intersection between the SWR circle. Okay, from the first step, you have draw the SWR circle. So you mark the intersection between the SWR circle and also the 1 plus JB circle. For example, like this. This is the SWR circle for the load and admittance. Okay, and then you mark the intersection as Y1 and Y2. Okay, and then draw a line from the center of the Smith chart to Y1 and Y2 and record the wavelength for each Y1 and Y2. So you extend the line from the center. Okay, look at the current position using WDTG, wavelength towards generator, and also Y2. And then calculate the D, the distance. Okay, so the two parameters that you need to identify in designing a single shunt stub is the D and also the L. So to find the D, you can compare the wavelength of the Y1 and Y2 to YL. So for example, your YL, your ZL is here, for example. So you got your YL somewhere there. Okay, so here you get the YL position, the lambda for YL, and here is the lambda for Y1, right? So you can calculate the D from the load to the stub. Okay, load to stub, so this is D1, and the other one from load to the second line, the second part. So here is lambda Y2, so you get your D2. Okay, by comparing the current position of the admittance, load admittance to the Y1 and Y2, right? So in this case, you'll be having two options, whether to use D1 or D2. Okay, and then to get the stub length L, okay, the stub length from the lines to the end of the stub. you need to record the real and imaginary part of y1 and y2. So here, just now you recorded the current position in wavelength. So now you need to record its position for real and imaginary part. For example, A plus JB, and here A minus JB. Okay. Alright, so then after that, you will perform the tuning or matching, impedance matching, by introducing the susceptance. You will introduce you will tune the imaginary part so that you can eliminate the imaginary part. For example, here is plus JB. So to eliminate this plus JB, so you can introduce negative JB. Right, so here is negative JB. To eliminate this point, you need to introduce plus JB so that it can cancel out. Alright, so then you can get a match positioned one there. Alright, so then after that, you can calculate the L1 and L2 from the short circuit point. Okay, in this case, it's shunt and short circuit, for example. So from the you need to be clear with the condition whether you are using the open stub or short circuit stub. If you are using short circuit, so then you use admittance. Shunt, for shunt you use admittance. So for short circuit, okay, this is the Smith chart. Okay, for impedance, we know that it will be equal to infinity, and it is open circuit for impedance. But for shunt, we use admittance. Here it will be equal to short circuit position. Okay, so at this point it will be Y open circuit. Okay, so calculate L1 and L2 from the short circuit position. So here is the short circuit position. So you get the L1 and L2. So here you get the okay, to get the L1 and L2, if the position of the if the position of the point that you introduce, positive JB, somewhere here, positive JB, okay, 0 plus JB. So you will calculate the length L1, JB1, so the length from the short circuit point. Okay, that gives you L1. So to easily calculate the L1, so if the JB1 position is less than 0.25 lambda, so you can calculate the L1 by simply adding the current position plus 0.25. If the position of JB1 is more, the value is more than 0.25 lambda, so you'll be subtracting, so the L2 will be equal to the current position minus 0.25 lambda. Okay, this is for short circuit. You are referring to this point. If it is open circuit stub, okay, so you'll be comparing to this point. Okay, so here it will be 0. So the L1 you can get straight away L1 here. Let's look at an example for single stub shunt. For a load impedance ZL equal to this value, design 2 single stub short circuit. Okay, it is shunt, so it is parallel, so this configuration, and then it is short circuit stub. Okay, short circuit stub. So we will be using admittance Y is of Z to match a load of Z0. Okay, Z0 equal to 50 ohm, assuming that the load is matched to 2 GHz frequency and consists of resistor and capacitor in series. Okay, so the first step to solve this is to get the normalized impedance. So 60 divided by 50 minus J80 divided by 50. So you will get 1.2 minus J 1.6. Okay, next you need to plot the ZL and draw the SWR circle. So your ZL is the normalized impedance just now is 1.2 minus J 1.6. So it's at the bottom and it's 1.2 here, and this is your ZL point. Then draw the SWR circle, okay, from the center of the Smith chart, and then plot the normalized admittance and mark its location using the towards generator wavelength, right? So from the center, so the opposite position, so this will be your YL, okay, and then mark the position of YL and also get the towards generator current position. Okay, next draw the 1 plus J beta, so 1 here plus J beta, so circulating that area. Okay, mark intersection between SWR circle and to the 1 plus JB, so the pink and the blue circle, look at the intersection point and mark it as Y1 and Y2. Okay, so now you have the intersection here, Y1 and also Y2, intersection between the two circles. And then draw the line from the center of the Smith chart to Y1 and Y2 and record the current location using WTG. So Y1, so you get 0.174, and then Y2 from the center, it's 0.324. Okay, at this point, 2, 4, there's some sort of mismatch a bit, maybe 2, 3 to 3. Okay, and then calculate D1 and D2 by comparing Y1 and Y2 to YL. So YL is here, so is here, and then Y1 is there, so you can get the D1. Right, so D1 equal to 174 minus 0.064, so this is your D1, and D2 is 0.324 minus 0.064, okay, towards generator. Alright, so in this case you have two options, whether to use D equal to 0.11 lambda or you want to use D2 0.26 lambda. Okay, so you have solved the D, now you need to get the L. Okay, so from earlier plot, so to get the L, first you need to record the real and imaginary of Y1 and Y2, the value of Y1 and Y2. Right, so Y1 equal to 1 and it's crossing at 1.4, positive 1.4. So this is your YL just now. Alright, so and then Y2, it is equal to 1 minus 1. This point, so it's minus 1.5. Okay, so once you have the Y1 and Y2 position, so to tune, right, to tune Y1, okay, so you want to make it a match position so that it can be just one, so one is match position here. So you need to introduce negative J 1.4 so that we can eliminate this, the imaginary part. So we introduce 0.0 minus J14, so minus J14 1.4, so it will be 24 is here. So we introduce minus J14 at this point, Okay, and then you draw a line to look at the current position of this this tuning. Okay, so this we can call it as B1. Okay, the susceptance value of the first admittance. Alright, so once you have this, then you can calculate the get its position. Okay, 0.348. Okay, here is 0.348. Okay, and then since this is the stub shunt and it is short circuit, so for shunt short circuit, here will be your short circuit position. It's 0.25. Look at the L value. If the L is larger than 0.25, so you'll be subtracting this value to 0.25. Okay, so since 348 is larger than 0.25, so you subtract them, then you'll get L1. The length of the first stub will be 0.098 lambda. Okay, next, same goes to the second Y2. So you have negative J. So to eliminate this, you need to introduce plus J 1.5. So introduce plus J 1.5. Okay, here is 1.4, here is 1.5, and then got the position. Okay, read through the value 0.3435. Here it's 0.156 lambda, and since it is lower than 0.25, so you will be adding both. Okay, 0.156 and 0.25, so you get 0.406. Okay, so from the earlier calculated value D1 and D2, so now you have two options, whether to use the first one by using D1, put the values in 0.11, and the length will be 0.098, or you want to use the second one with 0.26, and also the length is 0.406 lambda. Okay, and it is the short. If it is shunt but open, then you'll be comparing to this point, the open circuit. Okay, so the length will be from here to your to this point, to L2. Okay, and so on. Okay, for a single series stub, okay, so just now we have seen the shunt or the parallel stub. So now if you have a matching network introduced in between the transmission line and the load, and it is in series, either it is open or short circuit, so you may follow more or less the same steps. However, for series stub, we just simply use the impedance. Okay, so for impedance mix chart, you have the open circuit here and you have the short circuit here. Alright, so the first step, as usual, to normalize the ZL and then to draw the SWR circle. Next, you draw the 1 plus JX circle, so you have the reactance value, and then plot the intersection between the SWR circle to the 1 plus JX. So now you have two intersections, Z1 and Z2. Then you mark the position, or the current position of Z1 and Z2 to get the D. Okay, so record the position using wavelength towards generator, and then calculate D1 and D2 by comparing it to the position of load. Okay, so you need to compare the load to stub. Okay, load to stub location or position. And lastly, to get the stub length, as usual, you need to record the real and imaginary part of the Z1 and Z2. Then you introduce reactance, positive or negative J, to eliminate the imaginary parts. And then you can calculate from the open circuit if the stub is open circuit, or if you have a short circuit, then you have to calculate the L from the short circuit. Short circuit for impedance in the left, on the left hand side, and open circuit on the right hand side. Okay, let's look at an example for a single stub series. Okay, match a load impedance of ZL to this value to a 50 ohm line. So this is your characteristic impedance using a single series open circuit stub. So in this case, it is open circuit, assuming that the load is matched to 2 GHz frequency, and the load consists of resistor and inductor in series. Right, so as usual, the first step, you need to get the ZL, normalized ZL. So 100 divided by 50 plus J80 divided by 50, so you get 2 plus J 1.6. Then you plot this into the Smith chart and then draw the SWR circle. Okay, your ZL, the normalized ZL just now, equal to 2 plus J 1.6. So 2 plus J 1.6 is here. So this is your ZL. And then draw the SWR circle as usual. Center from the center of the Smith chart. And then draw the 1 plus JX circle. And then mark the intersection between both circles using Z1 and Z2. Okay, so you have Z1 and Z2. So Z1 on top and Z2 at the bottom. Next step is to get the L. So mark the location of ZL, Z1 and Z2 in using WTG. Right, so for Z1 it is 0.17 something, 0.171, and then for Z2 is 0.33 lambda. And then to get the D, so you can calculate the difference between the Z1 and Z2 to ZL. Alright, from the load to the stub. Okay, so this is your ZL to the stub in this direction, WTG direction. So load to stub. Okay, so load to stub for Z1. So if you look at the position to get D1, load to stub. So this is the load position. Okay, the load position to get it to the stub, the first stub, this one. Okay, so this is your D1. So D1 basically here is 0.5 minus this position 0.208, and then plus from here to here plus 0.171, so you get 0.463. And for D2 it's Z2 and also Z load. So it's from the load to Z2 to the stub. Okay, from the load to the stub, load to the second stub, to the second source of stub. Here, this is your D2. So it's 0.33 minus 0.208. So you get this value. So you have D1 equal to 0.463 lambda, and another one is 0.122 lambda. Okay, next is to find the L. Okay, so to get the L, first you need to record the position of Z1 and Z2. So Z1 is +1 plus J 1.3, and then Z2 is 1 minus J 1.3. So to eliminate the first component, so to eliminate this, so you need to introduce minus J 1.3. So minus J 1.3 will be at the bottom here. Okay, and then you get 8 blank. Okay, its wavelength here 0.335 something, 0.35245 lambda. Okay, and then you get the L from, this is the for the question, it is open circuit. For impedance, open circuit is here. So since the value is larger than 0.25, so you'll be subtracting 0.354 to 0.25, so you get the L1 equal to this. Okay, next, to eliminate for the second Z2, so you need to introduce plus J1.3. So plus J1.3 will be in that position. Okay, so its wavelength is 0.13146. Okay, 0.146, and to compare with open circuit impedance, so it is less, so you will be adding 0.146 plus 0.25, so you get the second length. So now you already have D1 and D2, so you include in the values into the figure, 04, 0.396, and the D from the earlier calculation. Okay, that's the end of the first part of the impedance matching technique. So I'll continue with the transformer and also the quarter wave length transformer and also the L section technique in the next video. Thank you.